One of the most common misunderstandings in the field of human performance, strength and conditioning, and muscle is the relationship between muscle mass and strength. Now, we've covered the back end on a separate video, which is what happens to strength when you add muscle mass. But I think the more interesting question is the opposite, right? Can you get stronger without getting bigger? In other words, adding more muscle mass. Now, this is important for people that are in weight-based class sports, like a wrestler or a boxer or even an Olympic weightlifter or a powerlifter, right? So they have to continue to get stronger, but they can't afford to add muscle mass. Or other people for 1,000 other reasons that don't want to add muscle, but they want to continue to get stronger. Well, anyone who has any education in this field is going to tell you the answer is, of course, yes. I mean, just look at the evidence. So we continually see people break powerlifting and weightlifting records, which means they're getting stronger and stronger and more effective in their sport, but they're not changing weight classes. But what's more important, though, and what we're really going to dive into in this installment of 55-Minute Physiology, is how that actually happens physiologically. All right, because we know the answer is yes. So what we really want to know is, how do I program such that I get the strength and power increases without adding muscle size? And then what's the physiology behind that? And of course, I'm always such a proponent of science, or I fundamentally believe if you understand the physiology behind it, understanding why the programming does what it does becomes unbelievably obvious. So let's dive into it. But before we do that, I want to take a quick second to remind you, this entire website and all these videos I do for free. Right, it's out there. I fundamentally believe everyone should have a chance to know this information. I think we're past the day of charging for basic information like this. And more importantly, I realize how fortunate I am. I'm in a country and I'm in a place and I have a job that pays me well above what I need to survive. But not everyone is in that situation. And so I make these videos so that all of you, no matter where you are in the world or socioeconomically, can have access to good quality health, fitness, performance, nutrition information. Having said that, there are a ton of costs associated with this. I actually am working on some things behind the scenes where I want to get some of these transcribed into shorter, quicker blogs so you can get to the information that you're interested in faster, some questions that you can use, because I know a lot of you are actually using this for your academic or even high school classes. And so I want to add more depth to this, and that just takes some costs because these things take me a tremendous amount of time. So if you're enjoying these or using these videos, I would hope, or I'm asking for you to go over to my Patreon page, and that's Andy Galpin. That's www.patreon.com/Andy Galpin, and just contribute $1 or $2. So that website works such that you can, set a maximum number of dollars that you can afford, say $2, $3 a month. And then you only donate based on when I deliver content. So you're not paying an annual subscription fee or anything like that, but if I post a new video, you get charged that $1 or $2. Or you can just set a monthly donation or just make a single donation. Every single penny that goes into that Patreon account goes back to one of these people that I pay to help me with this. Right? So I don't take any of it as personal salary at all. The more money we can generate on the back end, the more I can set up this infrastructure, and so I could fire out a lot of these videos a lot more often. My goal actually next year is to have a lot more of these videos up and answer user questions. So once again, if you can take that quick second to pop over to that account, Patreon, patreon.com/Andy Galpin, and help us contribute to spreading the word of science and health and performance, human performance and nutrition, I would appreciate it. All right, so enough of that. Let's get back into it. Well, anytime you want to answer a programming question, or really any question, I think we should turn to the experts. So in this particular case, who are the best in the world about getting stronger but not adding too much muscle mass? And again, we're thinking muscle mass because we're worried about people who either for aesthetic reasons or for any other reason don't want to add muscle or don't want to add weight, period, to the scale. So the best in the world of this clearly in general are the powerlifters and Olympic weightlifters. And probably if we're being technical, we'd have to hedge towards powerlifting because that sport is truly the test of strength, where of course weightlifting is more of a test of power, right? And so we want to look at these individuals. Here's a good example. This is my friend Steffi Cohen. Shout out Dr. Steffi Cohen now. She's one of the strongest women in the history of the world. She's got about 20 world records or something like that. I'm sorry if I messed that up. I know it's a ton. She competes at 123 pounds and is getting close to deadlifting 4.5 times her body weight, which is an insane amount. Hell, by the time you watch this, she's probably deadlifting 600 pounds at 125 pounds. So she continually throughout her career has gotten stronger and stronger and stronger, but she's still been able to stay in the same weight class. And so we want to look towards this community and say, hey, what are the types of programming things they tend to do and have and recommend that allow you to get stronger, faster, and more powerful without getting bigger? Well, the first answer is what we in the scientific community call the SAID principle. That acronym stands for Specific Adaptation to an Imposed Demand. What that means, if you want to get better at shooting free throws, the best thing you could ever do is shoot free throws. So if you want to get better at picking something up that you can't currently pick up, or pushing something, or pulling something, or dragging something, whatever it is you're trying to do, the most specific thing you could ever do to address that, programming-wise, would be to pick something up that you can barely pick up, or can't quite pick up, right? And so, in other words, very, very, very heavy things. So the adaptation is very specific to the demand. So if you look at two individuals that are doing two different types of workouts, what you can see is, imagine one of the girls here on the left, and the girl on the right, say they're doing different workouts, but they're both working equally hard, sleeping the same, eating the same. Well, they would see different physiological adaptations because of the specific adaptation or the demand being placed on the body at the time, right? So this programming stuff is important. In terms of how heavy you should lift, if you look at the bottom of the figure here, this is relative percent. Again, think this is what we call intensity, but think of this as how heavy, what percentage of our 1 rep max. Well, for general strength training, what we're talking about is something in this 80+% range. Now, obviously, we need to change this based upon your background, okay? This is just a general guideline, but the closer we can hedge ourselves to that 100, the better. Two other important notes here. Unless you have extensive training, and I mean 10 probably or more years doing heavy strength training, you can't just do 100% every single day, especially the same movement. You're going to break. So just think of this as concept, trying to get to this heavy stuff as often as you can, but still use periodization, still use appropriate program design, monitoring of volume, and all that stuff, right? But we just want to shift ourselves more towards that strength as much as we can. Point number 2, that's not a bad low-quality graphic, or that's not me being sloppy. I'm not sloppy in my PowerPoints. But do you notice how the strength actually goes past the 100? Well, we'll talk about in a second. There's several different ways when you can actually lift something that's quote-unquote greater than 100% of your 1 rep max. Things like heavy eccentrics or maybe using some assistance can be helpful. So generally anything in that kind of heavy, pretty heavy-ish range. If you're a beginner, more like say 5 years left of heavy lifting or less of heavy lifting, or maybe even none, you don't need to start at 80+% probably for strength. Even as little as 60% can be fine, right? So really imagine the scale is kind of sliding back and forth. But mostly, once you're fairly trained, 90-ish% a lot of the time is what we're looking for. So because we're trying to lift at a very, very high load, the number of repetitions per set has to be small, right? Probably less than 5 or 6 total. Again, there's always a gray area. There's no hard and fast lines. It's not like at 6 reps you get strength and 7 you get nothing. Or at 81% it's strength and 79% it's not strength. It's not that specific. But just think, we're trying to lift something very, very heavy, so because of that, we can only lift it a few times. So strength is down in that 1-to-6 ratio. In terms of order, now generally we want to do strength at the very beginning, and this goes back to basic program design principles. Do what's most important first. In this case, if the thing that's most important to you is building strength, and you're going to do other stuff, say hypertrophy work, or speed work, or conditioning work, well, conditioning especially needs to be done after the strength workout. Now there's plenty of other exceptions in other videos when I can explain to you when it's okay to do conditioning first. But in this particular instance, if strength is the primary goal, there are 2 main reasons why we want to do that before we would do any of our conditioning work. Number 1, if we're trying to do strength at the same time we're doing conditioning, so imagine doing intervals or doing a circuit or something like that, or trying to do conditioning before we do our strength training. Well, the primary problem with that is you're going to be tired. If you're tired, you can't lift something maximally heavy. Now that should make intuitive sense, right? If I ask you to pick something up that is the heaviest thing you could ever possibly pick up, well, I can almost guarantee you with very few exceptions, you can't do that if you're tired. That percentage, that maximal force you can produce is going to slide down by 2, 3, 4, 10, 15%, some number, but whatever that number is, if that number is 0.5%, well, that means you're 0.5% lower, and that's not 100. So we need you to be at a very high force production for strength training. So conditioning is going to compromise our ability to do things at a high velocity or high force, more specifically. which compromises that adaptation because now we're doing something kind of tiring at a kind of high force production, and that's not specificity. Number 2, in some cases, if you do a bunch of conditioning work before your strength stuff, you're now going to take your smaller muscle groups, or even any of your larger muscle groups, but a fatigued muscle group, and you're going to ask it to produce force in probably a compromising position under tremendous load. And that, my friends, is just a recipe for potential risk, right? A recipe for injury. So I'm not saying you can't ever. Certainly you can, especially as you become a more advanced athlete. But for the most part, we want to be very cautious. I'm not going to say never, but just cautious of how often we're going to do our conditioning before our strength work when the goal is strength, right? There's just really few reasons to do that stuff if the goal is strength. Okay, in terms of the movement, now, when you go to the gym, this is another one of those fundamental questions. People talk about, well, what are you doing in the gym today? And a lot of people like to do what we would call body part splits. So Mondays I do back and biceps, Tuesdays or triceps, Wednesdays or deltoids or things like this, right? You've heard, I'm sure. You've probably done it, right? I have done it tons of times. Well, that would be selecting the exercise that you're going to do for the day based on the muscle group. See that in the bottom in green? Sport coaches, strength and conditioning coaches generally tend to choose exercises not by the individual muscle group, but by the movement pattern, right? So are we trying to do a hinging movement? Are we doing a pressing movement? Are we doing a pulling movement? Are we doing a rotating movement? Well, both forms of exercise selection are valid, but it depends on the goal you're trying to get at. So in this particular case, when strength is the goal while trying to maintain or minimize muscle growth, we generally want to pick by the movement, right? We don't need to do isolated individual muscle work unless we've got a very specific physical therapy reason or an asymmetry or something. For just generally trying to get strong, we select the exercises based on the movement patterns. And then what we do is make sure we have a reasonable balance throughout the day and mostly at least throughout the week across all of our joints, across all of our ranges of motion in those joints. If you do that, you're going to be able to do strength training fairly frequently for a long time and not induce any asymmetry or overuse injuries because you're balancing the movement patterns, and that's what's most important for this area. All right, so a little more detail here. You can use a different system. I would encourage you, honestly, to generate your own system. I know a lot of other coaches that have a slightly different one, but I did want to give you an overview or some concepts of what some of these movement patterns might be. So for the legs, I like to think about it as being 3. There's squatting or pressing, hinging. This would be like a deadlift or an RDL, or pulling. Some people call that a lower body pull, right? So I'll often refer to, if I was doing deadlifts today, I'll say I did a bunch of pulling today, pulling from the floor, or like a clean pull or a snatch pull. Anything like that is still a lower body movement, but it's a hip hinging movement versus a squat movement. And then the third one is lunge. Some people like to call these single leg, and some people will split up lunging versus single leg because a lunge is technically not a single leg. Split squat, those are slightly different exercises, but those are the general categories of leg movements. In terms of the upper body, we've got 4. It's horizontal pressing and pulling, and then vertical pressing and pulling, and there's not a lot of other distinction behind those. In terms of the core, there is, of course, flexion and extension, and there's rotation, and then there's lateral flexion. Some people like to call this 6 categories because they'll say there's an anti-component. I kind of lump those in, so I don't care what you like to do. Just in your head, make sure that, hey, if you're doing a lot of flexion work, say like a crunchy, well, make sure you're also doing some what's called anti-flexion, which is avoiding flexion. So you don't want to flex when you don't want to flex. Anti-extension work, right? So doing extension work here, where you're actively going backwards, well, the core needs to be able to avoid unwanted extension. So some people call that anti-extension or anti-lateral flexion, right? So imagine doing like a single arm dumbbell, and dumbbell's pulling you down. Well, in this case, you're using your core muscles to not lateral flex, anti-flexion, versus actively flexing and pulling up, right? All 3 important ones. This other stuff can get a bit tricky. So the other ones I called it kind of total body movements, like snatching. It's a press, it's a pull, it's an overhead press, it's an anti-overhead, anti-flexion, it's all kinds of other stuff. Throwing, jumping, sprinting, rotating and pressing, landmines, complex movements. They don't necessarily fit into that category, right? So again, what we're just trying to highlight, don't think detail here, think concept. What we're trying to do is select our strength exercises such that the movement patterns that are typical of the human body are roughly equally balanced throughout our program, right? We just don't want to go long stretches where it's like, hey, I haven't done any horizontal rowing. This is why my shoulder's gotten gunky in the last 5 weeks. Weird. Or you look at your program and realize, boy, I'm doing a lot of lower body hinging, but I'm not doing any lower body pressing, no lower body squatting. Or it's all bilateral work, 2 legs. I haven't done any single leg work. Or whatever the case is. And you don't need to have a one-to-one match. You don't have to have exactly equal ratios between all these movement patterns. Just a reasonable pattern across the week, across the month, especially every couple of months. Make sure you look back and go, okay, it's been a while since I've done any rotational stuff here. I need to do some more anti-rotation work to strengthen myself up there. If you do all that, then you can put yourself together a nice little program. So what I like to do here, the famous saying that the concepts are few, but the methods are many. In the right hand or left hand column, whatever it is you're viewing this from, I'm going to go over those basic concepts of strength again, kind of a summary, and I'll add a couple extra points. And then on the right hand side, I'll give you a few methods, some of which you've probably heard of, but some maybe you haven't, right? Now again, the methods are infinite. I would encourage you to explore a bunch of them. Just as long as you're executing those methods, while hitting these concepts, you should have no problem getting stronger without adding too much muscle mass. So number one, complex movements like we just talked about, right? So we generally don't need to worry about doing forearm isolating work or brachioradialis specific work like that if the goal is as stated before. 3 to 20-ish sets per exercise, then it really depends, right? So if you're a beginner, of course, hedge more times 3. If you're advanced, maybe you can push it more towards 20. I'll give you an example for 2007 national championships in weightlifting. One of the things I did almost every day would be like 15 to 20 sets of 2 of a snatch, and then 12 to 15 sets of 2 of a clean and jerk, and then 15 or so sets of 2 or 3 or 1 of a front squat. Right? I was fairly advanced, competing at a reasonably high level there, and so I could do that. But it just depends on where your background is, right? So these numbers can be really good. We want to be paying attention, though, to what you can see in yellow there. All right, so it's still 1 to 5 reps per set. Now, I did a pretty famous podcast on Joe Rogan's platform a year ago or so, I think. And I talked about this, and so if you can go listen to that if you want a better explanation. But one thing we want to think about is the difference between something like 3 sets of 10 versus 10 sets of 3. So 3 sets of 10 is actually going to land you closer to what that optimal hypertrophy zone is. Even though the total amount of volume, 30 reps, is the same between both groups, 10 sets of 3 allows us to get what we call more first reps or more high quality reps. And I'll get into that in just a second when I talk about one of the methods. But that's really what we're talking about, okay? So use that number of sets as a sliding scale, depending also on how many days you're working out per week. So if you're working out your legs twice a week versus 4 times a week, well, you might be able to do less sets per day or per muscle group or per exercise, if you're working out more frequently. But if you're only doing legs once a week, you probably need to have more volume, right? Which there are probably few reasons why you should ever do legs once a week. Shame on you, right? Especially if strength is the goal. For bodybuilding or hypertrophy, maybe you get away with it. But basically everything else, we need frequency here. Like we said, 80 to 100%-ish plus of your 1 rep max has got to be heavy. We've already covered that point. We want to emphasize speed on all reps for the most part. I'll give you an exception to that in just a second. But let's remember, you're not probably going to move very fast because the force velocity curve tells us when things get heavy, you're going to go slower. So because you're going heavy, it's going to go slower. Fine, no problem. But there's also significant research that suggests that the interest or the effort trying to go fast is maybe more important than actually going fast. And so when the intent is to go fast, don't just do whatever is enough to move the weight. Make sure you're really trying to go as strong and hard as you possibly can. With all that being said, we want then maximal rest between each set. So we're not trying to do this for a conditioning piece. If you're extremely out of breath, if you're sweating, if you're throwing up afterwards, this is not proper maximizing strength training. You want 2 to 5 minutes between sets, maybe 7, 8, depending on how heavy it is, how many you're doing. Let that, be smart about that. It doesn't have to be magically in there, but the point is you want full maximal recovery. Okay, this also minimizes what's called metabolic damage or metabolic fatigue, which is one of the ways you can induce muscle hypertrophy. So if you stay nice and fresh, no burning, no tremendous fatigue happening, that should help you minimize the amount of muscle hypertrophy. So some of the methods. One of them, push, pulls, carries, presses, things we've already talked about, drag a big sled, push things up a hill, all very, very, very good. Negatives and eccentrics. This is one thing I actually wish I would have paid more attention to. I went like 10 or plus years without doing anything like this. But you've all done this, overload eccentrics, right? So if you can bench 100 pounds, maybe you put 105 pounds on and you just lower it to your chest, you have friends lift it back up, and then you go back down. Those are called negatives, or heavy eccentric work. Very, very good for strength. Now be careful though. Be careful on these for two reasons. They're pretty good at inducing hypertrophy, and two, they're very damaging. You're going to get really sore. So don't use these things too often. You can still pepper them in though once in a while, and they're very, very, very good for strength. Alongside that, isometrics. I would encourage you to check out Cal Dietz and his triphasic program. But the same thing here, I regret going probably 15 years without doing really any eccentric work or isometric work because I was too concerned about moving slow. I didn't want to teach myself to be slow as a performance athlete. But I could have peppered them in, right? I could have done it every once in a while, thrown in a couple of sets here, done a 6-week block here or there. That wouldn't have really made me slow over the course of the year. The isometrics and the eccentrics are particularly good for movement control, movement quality, for learning, for motor control, for technique, as well as for the connective tissue, the ligaments and joints and things like that. So that I think is a very, very important component to strength development. Weightlifting movements, of course, so this would be Olympic weightlifting, snatch, clean and jerks, variations, push presses, high pulls, things like that, all very, very, very good. Dynamic variable resistance is another one. Some people also call this compensatory acceleration. You may have heard of it just simply as like heavy bands and chains. I'm not talking about those little TheraBands. I'm talking real thick, heavy elastic bands. You can squat, deadlift, bench with them, things like that. We've run some studies in our laboratory specifically, and a couple have been done in some other places across the country. And these things are quite effective at strength development. So they're very, very good for force production. And I think Louis Simmons and all the folks in the powerlifting community have shown us 20 or 30 plus years of anecdotal evidence on this, and they're very good for strength development. You can, maybe I'll make a separate video for that if you'd like, let me know. Leave a comment or send me a note if you want a 5-minute phys maybe on dynamic variable resistance or accommodating resistance, sometimes called compensatory acceleration, all kinds of different names for it. But that's a very good tactic. I would encourage people to put that stuff in, even if you're new. So even for people that are just getting into strength training, it still is going to require some very good control and stabilization, so it's a good thing in general. And then lastly, what are called cluster sets. So this is another thing that have probably got 20, maybe 30 studies showing these are very, very effective. I'm sure most of you haven't heard of these though, so let me walk you through what that means. So imagine you're doing what we call a traditional set, 3 sets of 5 repetitions. How that would work is you're going to do 1, 2, 3, 4, 5 reps in a row, right? Then you take your 2 to 5 minute break, and then you do 1, 2, 3, 4, 5 reps in a row, 2-minute break, 1, 2, 3, 4, 5, and that's your 3 sets of 5. Well, with the cluster set, it's the exact same program design, so you don't have to change your program. You can still do 3 sets of 5 or whatever set range you're doing. It doesn't matter if it's 5 sets of 3 or whatever, 10 sets of 2, who cares, right? Well, the difference is with the cluster, you're going to take a little mini break, about 10 to 15 to 20 seconds between each repetition. And then you'll still take your 2 to 5 minute break in between the set, but there'll be a repetition break. So what it would look like is something like this. 1 rep, sort of shake it all out, 10, 20 seconds. 1 rep, shake it all out. Do your 5 reps, take your 2 to 5 minute break, and then do that over and over and over again. It's funny because in the weightlifting community, this is like what you do anyways, right? So you do a snatch, and then you drop it down, and it's like, okay, shake it out, reset your grip, put the weights back in line them back up, boom, do another rep. And then you drop the bar, shake it all out, line it, boom, do another rep. And then all of a sudden you're like, great, like triple PR. Like, what? That's 3 reps? It took you a minute to do 3 reps. Well, by nature, almost always weightlifters tend to do cluster sets. But again, like I said, there is strong scientific evidence to support these things are as, if not more effective at strength development than traditional sets. And as I mentioned, they also reduce the metabolic disturbance or the fatigue, which can help mitigate hypertrophy. So a very, very good technique to utilize. That being said, let's talk now about the physiology, what actually explains how I get stronger. Once you understand this, you don't have to memorize that programming stuff because it actually all explains itself. So let's have a little fun now and talk about the physiology of getting stronger without adding a ton of muscle mass. All right, now there's 4 separate categories I'm going to get into today. Number 1, the nervous system is probably what you've heard about. If you're a strength and conditioning coach or a student, it's in any of your textbooks or your certification exams. But 2, 3, and 4 tend to be forgotten or simply not known. So let's dive into each one of these one by one. Number 1, the nervous system. So we see significant adaptations at the level of the central and peripheral nervous system that allow us to enhance force production, again being stronger, without necessarily adding muscle mass or being hypertrophy. So number 1, to start us off, basic physiology and anatomy tells us there's what's called a motor unit. And so you can see an actual picture of it right here. You remember the basic anatomy of a motor unit. And so a motor unit consists of an alpha motor neuron and all the muscle fibers that it innervates. And so a nerve comes down and innervates or activates a whole bunch of muscle fibers. That section together is what's that motor unit. Now what we have is what's called the all or none principle. And what this says is anytime that motor unit is activated, it contracts fully and it activates every single muscle fiber in its motor unit fully. Right, so you can't turn a nerve like 3/4 on. You can't turn a nerve on and tell it to activate 10 of its muscle fibers or only 12 of them. It fires at full strength and it activates all the muscle fibers. It's called the all or none principle. Right, so to use the analogy of like a light switch, okay, now imagine a motor unit functions like a light switch. When you move that light switch 20%, it's still totally dark. But whenever you break that seal, boom, it goes to 100% light. Right? It's not like a dimmer where you can go up 20%, 25%, 30%. It is 0, 0, 0, 0, 100, 100, 100, 100, 100, 100, 100, 100, 100, 100, 100, 100, 0. Right? It's all or none principle. Okay, so what that means is the only way that we can enhance force production, whether that's acutely or chronically, is to activate more motor units, to turn more nerves on. So an example here, if I were to take this pen and I wanted to scratch my eyeball, oh my God, that's kind of scary, right? Well, I wouldn't want to have every single motor unit in my bicep being turned on there because then I'd be contracting at full speed. I'm going to start off any movement by activating the least and smallest amount of motor units possible. And only under one circumstance do I activate more. And that's when my body is put under a situation in which the requirements for force are higher. So if I were to add another thing to this list, force requirements go up. Now I activate more motor units. If I were to add a 10-pound weight to there, more motor units would go on. And so what happens is the vast majority of our motor units are not being used. As we add more force production requirements, I add more, activate more, and more and more and more. This is, again, very common ex-phys if you've had this class before. Right, so you can see there's a little image. You see a little lightning bolt. It starts off in the basic part of the neuron. It activates, it goes down. You should all remember your basic anatomy from here, right? The myelin sheath, how it's jumping from node to node, going down from the axon, or coming from the dendrites, and goes all the way down, and it innervates in each individual nerve. So let's give you a practical example. Imagine you're like my friend Doug here, and he's trying to deadlift, I think that was 220 kilos or something like that. 500 pounds-ish, right? As he starts to pull on that barbell, he's initially only activating a small percentage of his motor neurons. But as his body realizes he needs more force production, he's going to turn on more motor neurons and more motor neurons. And eventually, if he turns on enough neurons, he'll have enough force production to actually start moving that barbell, right? And that's how all strength training happens. So 1A, the first adaptation that we get is an increase in motor unit activation, right? But only when more force is required. So the only way to get stronger is specificity. Pick up heavy things, right? You don't get this from anything else. So here you go. Here's an example. Take a look at him right here. Boom. Perfect, right? Did you notice that? Pretty subtle, but we'll watch it one more time. See at the bottom here, he starts to try to lift the barbell and he realizes not enough, not enough, not enough, more neurons eventually, and then you literally see that physiologic phenomenon happen right in front of your face. Right? That's shout out to Doug Larson from Barbell Shrug. Go check him out. Douglas E. Larson, I think, something like that on Instagram. You can give him a follow. Right? But that's a primary example of this physiological phenomenon of needing to activate more motor units. Right? And well, what this is it's an explanation, or it's a predecessor, or precursor, rather, for what's called the size principle. Now, the size principle is founded by one of my favorite scientists of all time, Eldwood Henneman. He's like your favorite grandpa, right? Like, look at him. You know that guy has Werther's Originals in his front room, right? Fantastic guy, like just the most warm, loving, amazing guy. Well, he put out a series of publications in 1955 and 1956, and he basically said, look, throughout the nervous system, the susceptibility of neurons to discharge is a function of their size. Translation? The smaller the neurons, the more likely they are to discharge or fire. Here's an example. When the body sends out a signal, it sends it out to all the neurons from the central nervous system, brain, spinal cord, right? Well, how does it know which neurons to send it to? Well, it really doesn't care. It just kind of sends it to all of them. Well, some of your nerves, the ones that tend to be smaller, are more susceptible to fire when stimulated. The bigger nerves need more stimulus to actually fire. So, smaller neurons are the ones that tend to go first. So to go back to our pencil, when I went to do this, what am I firing? Small or large neurons? It's the small ones, right? If I want to fire the bigger neurons, since they're less likely to fire, I have to give them tremendous stimulus. I have to really tell them, I really need your help right now. Please come and give me help. Right? So as we go through the sequence of pictures here, and we start out the bottom left-hand corner and we move our way to the middle and to the top, here's what we see. We see we have activated small to bigger neurons. All right? Now, what would happen if we did the opposite? What would happen if we started with big to small neurons? You see, it wouldn't work, right? Because I wouldn't be able to lift up this pencil without just doing that every single time. Because I can't turn down the dimmer switch. They're all on or they're all off. So I have to go from this small to big neurons. This is called the size principle again, right? I go from small to big. And so if you look in this picture, what we're seeing is basically I've graphically depicted the same thing. So force production on the bottom and recruitment threshold on the side. And imagine those are each individual muscle fibers or motor units. It doesn't particularly matter. It's going to work the same. Well, your muscles don't actually just kind of turn everything on. And they're not all the same size and exact same shape. So at low levels of force production, bottom left, we have low recruitment threshold. That was Doug at the very bottom, right? Didn't think he needed a ton of force production. He started pulling, he started activating bigger, higher threshold neurons, and force production went up, so he first started to get that barbell to move. Then, once he really activated the super big, super fast neurons, or motor units, he finally was able to generate enough force production to where he could finally lift the barbell up in the air. All right, so this is really what we call 1C, if you're going back to that original slide. So what can happen is, in addition to activating more motor neurons, this would allow you to produce more force, right? In addition to activating the bigger motor neurons, so really that's two adaptations, right? Just turning more neurons on and activating bigger ones. The third one, which is why we call it 1C, is the rate of motor unit activation. Now this is going to get a bit trippy and somewhat psychedelic here, so don't tell Mike Bledsoe on me. But like I said, the nerves aren't just like on. They kind of actually cycle back on and off, on and off, on and off, the neighboring ones. And so here's what it looks like. You can see the kind of animation like that. So even the low threshold ones would be cycling on and off. And as we go past them and go into further, even up to the larger ones, this is really what it would look like, right? Well, one of the adaptations that you're theoretically able to get through strength training is you can increase the rate at which they're starting and stopping. So in the animation, all I've done is change the cycling time on that animation, from once every half a second to 10 times that speed, and watch what happens. Okay, now I literally graphically or technologically just did that by changing the frequency in which that animation happens, making it more rapid. Well, that's exactly what happens with your motor unit activation. You increase the rate of activation, you're faster at doing that. So because of that, you get that helicopter propeller effect, right? Where it looks like you contract the propeller because it's going so fast it actually catches back up, right? Well, when you do this, you're able to generate more total force production, particularly in terms of human movement. Right? And then finally, 1D is you get an increased synchronization within and across muscle groups. So what that means is basically this is a technique issue, right? It's a neuromuscular technique. So as you go to do your deadlift or do your overhead press or whatever it is you're doing, you learn to turn on more motor units. You turn on bigger ones. They cycle on faster, but you also learn exactly what order to turn which ones on, right? So you start using more deltoid here, and then the deltoid kind of peters away so you can give more energy to the tricep or whatever it happens to be. So the motor units within each muscle group, just within the individual tricep muscle or the deltoid muscle, they're better off understanding when they need to apply force and when they don't. When they need to save energy and when they really need to give it. And they're also more likely to take it from a muscle that doesn't need it and give it to the specific ones to do. So you just get more neuromuscularly efficient in your movement. And that's really what it comes down to. Okay, so that's nerve, number of motor units activated, size principle, right? Type 1, 2, and 2x. These are slow and fast and super fast twitch. Rate of motor unit activation and motor unit synchronization. The next big thing is muscle length. So we're still on a nerve here, and there's a reason, okay? This one's particularly complicated. It's been taught often, you've probably heard about it, but I almost guarantee you it's been taught to you wrong. So let's dive into this muscle length issue. While we're here, let's differentiate when I say putting a muscle on stretch. Okay? So I'm not talking about stretching your muscle. I'm saying putting it like on an acute stretch. Right? So when we say muscle length here, we're not talking about if I get more flexibility in my hamstring. I'm talking about on this position versus that position. Okay? Make that difference. Right? Maybe we'll do a separate video on stretching or something if you want later. Okay, so the muscle length determines force production, right? Because of what's called the length-tension relationship. Now this is a figure up here from the actual original paper, and it's really, really cool. So you remember from basic anatomy that it's called a sarcomere. Okay, that's the smallest functional unit of a muscle cell. So think individual muscle cell. Don't think my quad. Think the individual cell within it. Okay, and what this chart beautifully shows you is the same force curve, actually, that I showed you earlier. But what it depicts is force production over length. So at the bottom left-hand corner there, you see that at a small sarcomere length, there's no force production. And what happens? That's 0.5 on the graph. What happens as we get to 0.4, 3, and 2? As I increase the length of the muscle, force production goes way up, right? Until I stretch too far, and then force production comes down. So the length-tension relationship tells us at the level of the sarcomere, again, just the muscle fiber, there's an optimal length for force production. Too small and too long are not good, but somewhere in the middle allows you to generate the most force production. You can see the actual image there, but this is why. Right? If you've had anatomy class, if you haven't, go back and review on your own. Right? But if you're one of my students, I know you've had this already in ex-phys class. But you remember the sliding filament theory, right? So the myosin and actin, right? The myosin reach up, grab the actin, contract, pull it together, right? We'll take a look at the images here. Now it's kind of a bit backwards here because remember 5 is on the left and 1's on the 2. But in number 1, which is the far right, if you're too stretched out, literally the myosin can't reach the actin. I can't produce force if I can't connect the myosin to the actin because that has to do my power stroke and pull everything together, right? As I get shorter then, so this is 2, 3, and 4 here in the middle on the bottom section, myosin can contract well with actin and cause good force production. But number 5 also has no force production because the myosin and actin are already up next to each other as high as I can get. So I can't smash them together any further. So here, myosin and actin too close together. Here, good distance, good powerful power stroke. Here, too long, can't reach each other. We've got problems, right? Well, This is a length-tension relationship. Now remember, this is length tension. It specifically and only refers to the sarcomere. This is actually, these experiments were originally done in, I think, frog muscle. They isolated the frog muscle, put it in a petri dish, and found this stuff out. But that's not how whole muscle contracts. And so yes, length tension is important, but that's not exactly how whole muscle function works. So if we look at anatomical position, right? You all know this from basic anatomy. Every muscle in the anatomical position is at what we call resting length. All right? So LT, length tension relationship, is optimized for every angle at muscle resting length, aka anatomical position. So if I'm standing here like this, all of those muscles, for the most part in my body, are at that equal distance in the middle. They're not too smashed together, they're not too stretched apart. But length tensionship doesn't account for nerve, it doesn't account for connective tissue or biomechanics. And so that in and of itself doesn't tell me everything I need to know about muscle contraction. And let's be real, all of us are here because we care about what makes the barbell or the dumbbell or the wheel or whatever, or the car, whatever we're pushing move, right? So we can't over-interpret length-tension relationship. What commonly happens here is people read, they learn a little bit about length-tension relationship. They think, therefore, muscle contraction is optimal in the middle, therefore I'm going to do my work like this. Never too small, never too high, no full range of motion, because this is where the most force production happens. Well, that's a gross misunderstanding of what the length-tension relationship can actually tell us, because it doesn't account for nerve, connective, or biomechanics. So let me show you what that means. Here's another image. Okay, so muscle doesn't move bone. Muscle goes into connective tissue, fascia, into a tendon. Tendon connects into bone. Okay, so look at the color coding there. In blue, skeletal muscle. In red, tendon and fascia. Okay, so here's what really happens. Whole muscle force production is that length-tension relationship combined with those elastic components, the tendon and the fascia. Right? If you take whatever muscle did, combine that with however well you transferred that force through the connective tissue to the bone, that will determine whole muscle force production, because that determines what actually moved the bone, right? Which is bone then moves implement. So let's combine all these things. Going back to this original length-tension relationship, just like I described, this is that same white, black and white figure thing. I just kind of made an updated version. Here's what it basically says. At resting length, in the middle, we have our contractile tension. Now when I say contractile tension, think muscle contraction, length tension relationship. And that's that inverted U, right? Boom. This is the same slide from a couple of slides ago that was in black and white, okay? Too small, contract actin, myosin together. Too far apart, can't reach. Optimal strength, force production in the middle. But at resting length, since the elastic part is like a rubber band, okay, at rest, there's not any tension in a rubber band. Okay, unlike muscle, at rest, there's already a tremendous amount of tension there. It's possible, right? And as I stretch a rubber band, is there an optimal length-tension relationship with a rubber band? No. The more you pull the rubber band, the more force production goes into it until it snaps, right? And so that actually looks just like that. You keep applying stretch to a tendon, it'll continue to increase its force production, right? Just do your bicep. Pull it back like that, let it go. It's going to fly back, right? The tendon wants to go back to resting length. Everything wants to go back to resting length. So when we do a whole body contraction, whatever it's going to be, like a punch, right? And we're going through here. While I'm overstretched here, I'm in a poor length-tension relationship, but every ounce of stretch I get here increases elastic tension, right? As I start contracting, I lose elastic tension, but as I get more to resting length, I gain resting length, right? So what I can do to maximize total muscle force production is combine my elastic with my contractile tension. I can't just go from here because I'm not going to be getting any extra advantage from a rubber band, right? Anyone that knows this would punch if the person wasn't moving by putting your muscle on the biggest stretch possible. I would turn my hips first because that actually disassociates the joints, which is another way of saying I put this thing on stretch by just moving the lower half and keeping this in the same spot. And now I get the most force production. So total overall tension looks like that. right? So with almost any human movement, from the muscle's perspective, now we haven't accounted for biomechanics yet, or mechanical advantage. It's like, hold on. But from the muscle's perspective, the take-home message I'm saying here is more stretch, more force production. All right? Now, there's cons to that. That's how we pull a hamstring if we're overstriding, right? And our leg, Brian McKenzie's taught us that, right? If we're overstriding and our foot's flailing way back, since we are getting so much more force production, boom, we can pull a hamstring. But this is really what it's about. You want to maximize force production. You want to combine the contractile with the elastic elements. And yes, when you move past resting, even though I start to lose contractile tension, I gain more elastic tension than I lose in contractile, so my net force production keeps going up. Imagine it like this. You are running to do a sprint, and a couple of steps into it, I get behind you and push you a little bit extra. Well, you're going so much faster by the time you get back to resting length because you used elastic tension to get started. You're going so much faster, I can generate more total force or speed or power or whatever I'm trying to produce because I use that elastic tension. Okay? And so this can all be summarized in what I call one of my major laws of strength conditioning, which is to say that we should generally train all of our joints through all of our ranges of motion because of this, right? Now, there's a bunch of other reasons to do that, and I said generally, not always, but for the most part, we want to train all of our joints through all of our range of motions for three primary reasons. Number one, we want to maintain the range of motion, right? You don't use it, you're eventually going to lose it. The easiest way to become flexible and mobile is to never lose it in the first place, right? So the more we train through big ranges of motion, the more we're likely to keep those ranges of motion, right? I'm never asking you to do a range of motion that puts you in a bad position, right? So I don't want a joint in a bad position. This would specifically be things like the lumbar spine, potentially the knee. But for the most part, go through your anatomy and understand the ranges of motion that occur in each joint, and then think, in my training, am I going through those full ranges of motion? If you are, it's good. If the joint is supposed to go there, then it's good. The reason why like a valgus collapse is bad for our knees is because the knee is supposed to do flex and extend. It's not supposed to go that way. So that way type of movement's bad. But the full flexion extension is great for the knee. It's full range of motion. Number two, it'll help you activate all or most musculature. Now I'll cover that in a separate video, but that's an important point. We need to be able to activate all the musculature. Joints that cross multiple joints aren't fully activated when one of those joints is slack. Okay, so it's a bit wordy, but trust me on that one. So full range of motion helps us activate all musculature. And then the last one, which is what we just covered and we spent extensive time on. All right, so more stretch is more force. Why? Because the elastic response is passive and subconscious. In other words, if you take your finger and you were to put it on a table and snap it like that, well, you're using the elasticity in that tendon, in the muscle, in the finger right there, right? It's passive. It's not burning ATP. There's no bioenergetics involved. It's just returning back to normal. It's a rubber band snapping, okay? And it's subconscious, right? Think of the Achilles when you're running. If you land heel first, or if you land on your foot, the elastic, the Achilles tendon, will give you a certain amount of force production and balance, and that saves you a ton of energy. Stretch shortening cycle is another one, right? So the stretch shortening cycle says anytime I've got my proprioception going on, anytime a muscle is stretched, it wants to respond by contracting, right? So if I then pre-stretch a muscle more, it inherently just wants to contract. That is active, it does take ATP, but it's also subconscious. So I can get more force production by just putting a muscle on stretch, right? This is why I would dip quickly before I would do a jump, things like that. And then C, like we said, the contractile tension. It's active, right? I'm active trying to contract my muscle. That's all somatic control. And it's conscious, right? So if we combine all three of those levels, A, B, and C, we're going to get the most force production possible. All right? So that's why we want to train all of our ranges of motion. So that's it for the nerve. Now let's transition, and it's much shorter here, to points 2, 3, and 4. But like I said, this is the part you probably have not heard before. So turning our attention to the more important or interesting stuff, just kidding, I'm a muscle guy, so I always think that stuff's better. Let's talk about muscle. So there are a host of adaptations that occur in muscle that allow you to be stronger without getting bigger. So I don't mean muscle hypertrophy. Right? People think that it's either nervous system, and that explains all the reasons why you get stronger, not bigger. But let's not forget the contribution that can happen in muscle. You probably need to go back and do yourself a thorough review of muscle structure and microanatomy, but I'm not going to do that here. I will fully expect that you understand the neuromuscular junction, how that works. And also, you should be able to review and walk yourself, say in an open essay form off the top of your head, how the entire action potential happens, how calcium is released, and how things neurotransmitters cross the neuromuscular junction. They open those sodium ligand-gated open channels and things like that. What acetylcholine is, what it does, how it's recycled, what acetylcholinesterase does. All that stuff should be important. You should also be able to continue from there and explain, or off the top of your head, how calcium is released from the sarcoplasmic reticulum, the action potential travels down the T-tubules, and then that whole sliding filament theory thing, right? So troponin, tropomyosin causing conformational changes, how the power stroke happens, the role of ATPase and all that stuff, and then how it's reset and what happens. I don't think memorizing the voltage and all that stuff is particularly important, but just at least the functionality of what actually occurs here is very important. While we're at it, I think it may do most people a bit of help here to take a look at the Z lines and the M discs and all that microanatomy structure, where everything lines in troponin, tropomyosin, like I said before, but even what's the thick or thin filaments, what's titin, what's nebulin, Z disc. If you take any certification in this field, strength and conditioning, particularly like the CSCS from the NSCA, they're going to ask you a lot of questions about that. So I'm not going to waste your time going through that here. I'm just going to have to assume you know some of this knowledge. But this is all good stuff that you tend to get asked on a lot of these common certifications, right? And then new ATP hydrolysis and all that stuff, okay? But more importantly, let's take a look at the big picture here. Regardless of what you're trying to do, you have to generate ATP. That's our only energy currency in all of biology, all of living cells, right? Whether you're using phosphocreatine, carbohydrate, fat, or protein. I've covered this in other videos, right? You can go back and take a look at this. We're all trying to get to ATP. Once you get to ATP, you want to split it into ATP, inorganic phosphate, and that releases heat, a whole bunch of energy, or a whole bunch of heat, sorry, and a little bit of energy. And then we use that energy to power things like muscle contraction and performance. Okay, well, here's what can happen there. You can get tremendous increases in efficiency at that muscle energy level. For example, you can store a lot more creatine phosphate. That allows you to produce more force more frequently. And virtually anything that I just covered, and all of it, adapts to strength training. Right? So for example, the calcium in the sarcoplasmic reticulum, it gets released sooner when you're more strength trained. And it's more sensitive. The affinity to calcium on the troponin tropomyosin complex on the myosin head, it's higher. You increase the amount of acetylcholine you have. You increase the amount of receptors you have at the cell. T-tubules get larger. Every single part of that equation has been shown at some level to increase, or whatever the change is to make the system more efficient, with strength training. So this is why I'm not going to walk you through all of those things. That would be another like 3 hours of video, right? But basically everything in that chain, if you were to ever be asked a question about how would from the cellular energy perspective increase force production, as long as you walk through any step, basically pick it and say it changes, it increases with chronic strength training, there's at least some mild, depending on some of the stuff, very strong evidence to show that that actually is the case. And so all of those changes, again, allow that muscle cell to produce and contract with more force. It doesn't necessarily make it any bigger. It doesn't have to just be larger and have a greater cross-sectional area. So number 2B then, fiber type. And this is also synonymous with contraction velocity, right? There's a reason we call it a fast twitch, because it twitches, ready for it, faster, right? But here you go. This is what our lab does. If this is the first video you've seen from me, you're going to get to know it, but if not, this is the primary thing I emphasize. So what you're seeing actually right there in the far corner is a muscle sample from a muscle biopsy. And you can see in the bottom all those individual muscle cells that are just sort of hanging out. Right? And so this is what we do, is we take muscle samples from people, we pull out cells one at a time, and then we can analyze those things for their fiber type, fast, slow twitch, things like that. Well, this is actually an image. It's kind of dark, but it's dark on purpose. You see that little purple line in the corner, vertical line? That's actually our laser scanning confocal microscope with my colleague Jimmy Bagley, and that's actually firing through one individual muscle cell on a glass plate, and we're taking some really high def, very zoomed in 3D images of a muscle fiber. Right? But regardless, in terms of fiber type, depending on where you've been taught or where you've read, you may have heard that we can convert fast to slow twitch, or slow to fast, or neither, or both, or something weird. Well, I'm here to tell you, as, sorry for the arrogance, but one of the world's foremost leaders in muscle fiber type transitions with exercise. It's very clear it happens in all directions. And it's very specific to the type of exercise you do. It goes back to SAID, right? It basically looks like this, right? This is my friend Mike Bledsoe, another barbell shrugged. Look at him lining up there. But here's an example. If you take a normal person's quadricep, typically they're about 50% fast twitch and 50% slow twitch. If you look at another muscle, say the soleus, which is the calf muscle, the anti-gravity postural muscle, that's like 80% slow twitch, maybe even higher. All right, so every individual muscle has a different fiber type composition. And what we call in muscle biology, structure and function follow each other. So, for example, if you look like at the quad, it's 50% fast, 50% slow. That generally means it helps with slow twitch type of things, which are standing up all day, walking. But it can also help with high power, high force things like jumping. The soleus is pretty much there to keep you vertical all day, to keep you walking all day. And it's not really needed for or helpful for force production. Its little neighbor, though, the gastroc, that other big calf muscle, is almost the inverse. It's almost entirely slow twitch. So the gastroc is there for sprinting and jumping, but the soleus is there to keep you vertical and erect all day. Well, we also see tremendous person-to-person differences. So we have had people in my laboratory that are 90% slow twitch in their quad. In that exact same muscle group, and by quad I mean specifically vastus lateralis, the BL muscle, the outside one. I have biopsied other people that are 90% fast twitch. And so really you can run the gamut in the exact same muscle, whether it's you or Hercules, right? There may be a different composition of these fast or slow twitch fibers. And so this is an example. This is from, again, Jimmy Bagley's work. He published this in 2012. So really what we see is this continuum. Okay, so on one hand you have the type 1s, which are the very slow twitch fibers. You can see them in image there. They're very slow, but they have a tremendous endurance. On the other end of the spectrum, you see type 2X, which are extremely fast and are very glycolytic, which means they use carbohydrates very well for energy. But they fatigue very quickly. And then we have what we would call hybrid fibers that are in the middle. So see that slow fast and that fast ultra fast? Those are single individual muscle cells that co-express either, in this case, that's half fast, half slow, or half fast, half ultra fast. Now, I'm not going to get any more details here. I have like a 2.5-hour video on this topic up. You can go check other videos. I actually have a 5-minute version of the fiber type stuff as well, so you can go check that stuff out there. But effectively what you're looking at is this. When you do steady state endurance type of work, you increase the amount of slow twitch fibers you have. Again, clearly shown. Depending on what you do, you may decrease or not change the amount of slow twitch you have. If you do something more, again, this is Mike Bledsoe. This is fantastic. By the way, I don't think he even knows I have this photo. You think it's bad doing bicep curls in the squat rack. Try doing bicep curls in the glute ham raise machine. Come on, man. But if you know Mike or you've heard of him, go tag him and tell him about this. He's going to be so confused and not know what's going on. But I don't think he even knows I have this picture. Point is, if you do like the classic hypertrophy, 3 sets of 10, things like that, you will see an increase in slow twitch and fast twitch fibers with a specific decrease in those hybrid fibers. More plyometric, true speed stuff, certainly see an increase in fast twitch with probably no increase in slow twitch. But what we don't know a tremendous amount about is anything else. I don't know a lot about intervals. I don't know a lot about circuits. We don't know a lot about strength training or different types of strength training or powerlifting training versus weightlifting training. We just simply don't know. We haven't done a lot of interventions. I don't mean we have, just the field hasn't done interventions there. So at the surface level, this is basically what we're looking about. So if you're to put this together, if you likely did some pure strength training like I talked about in the beginning with the prescription, you would almost surely see an increase in the amount of fast twitch fibers you have. If you do that, you should be able to generate a lot more force without necessarily being any bigger. Now, typically fast twitch fibers are oftentimes bigger than the slow twitch, but not necessarily. Just changing its type doesn't itself increase its size. And I'll give you a good example. What we can do in our lab is we can take these individual fibers and put them up into a little petri dish, tie them to the end of a force transducer, and we can measure its individual force production outside of the body. So what we typically see is, you can see this, the MHC 1s versus the 2As. So the 1s or the 2As are typically much more powerful at the single fiber level than the 1s. Fast twitch versus slow twitch. No surprise the fast twitch has more power than the slow twitch. But what most people don't understand is that contractility can increase in both fiber types post-chronic strength training. So take a look at the type 1s. Even the ones that didn't convert to 2A, the ones that stay at a type 1, can get more powerful, independent of size. They can simply produce more force through the mechanisms I talked about in point A, right? All those microanatomy things happen that can improve efficiency and power production independent of size. The 2As as well. So if we look at muscle combined, we have multiple scenarios here. The energy stuff, the fiber type can transition, or we can simply produce more force or power, all without necessarily just getting bigger. So one of my other important laws that we'll talk about in my classes a lot is muscle is extremely plastic. Virtually every single thing that we know of how it functions changes with training. So that brings out a thing that people hear commonly, which is what we call our early versus late strength adaptations. This is a fancy way of saying, how is it when you take someone and they've only been lifting for, say, 2 or 3 weeks, or maybe even a week, and all of a sudden they're stronger? Well, it's not because of hypertrophy, of course. What is it then? What's that you say? Everyone wants to say, the answer is because of neurological. And while that is true, as I just outlined, don't give all of the benefit to the nerve system. There's a lot of muscular adaptations that happen that allow you to also be stronger very quickly without necessarily being any bigger. So typically, those first 4 to 10 or 12 weeks or whatever you want to call it, those adaptations that allow you to be stronger and before you've actually put on any additional muscle mass are mainly neurological. We talked about a number of them, right? Frequency of firing. You also have things like increased relaxation of antagonist muscle groups. So what you may not realize is during a bicep curl, your tricep, the antagonist, actually fires. One of the adaptations you learn quickly is to relax your tricep, right? Because if you fired your bicep at the same time you fired your tricep, you wouldn't move. So by simply relaxing your tricep, that allows you to move the bicep more effectively. Any change in that neuromuscular junction side, right? So in those microanatomy, synaptic vesicles increasing, acetylcholine, all that stuff. Or decreases in GTO, Golgi tendon organ resistance. That's very similar to what I was saying earlier. The GTOs measure tension. And when they measure and they realize tension is occurring, they respond by turning the muscle contraction off. And so that can happen as well. But like I said, they're not all neurological, so don't forget about those changes in calcium kinetics and muscular junction stuff, fiber type, or contractility that can produce more force. Our last couple of points here, 3 and 4, very quick, just because we've already exhausted the topic. Connective tissue is sort of the forgotten child here, so we can clearly have increases and decreases in efficiency of force transfer through the connective tissue. We just don't have much research, and we don't understand how well this can be done with an intervention like strength training. Same thing with mechanical advantage, all right? So the last final point here, I'm ignoring biomechanics for basically all of this, right? So you can look into that field, but if you change mechanical advantage, pennation angle, all this stuff matters, and all these things, pennation angle specifically does change with training, and this is the angle at which your muscle lands into the the angle at which your muscle lands in the bone. Okay, so if you change that angle one way, it favors range of motion and speed. If it goes the opposite direction, it favors force production. This can influence general force production as well without necessarily being any bigger. Limb length changes, changes in technique that alter mechanical advantage versus disadvantage, things like that. So you can go then and learn about your class 1, 2, and 3 levers. If you take a certification exam, you need to know it. Not in my classes ever. But things like this are important and relevant to the conversation. So that being said, hopefully you've learned more in this short video. about how you can get stronger without adding any additional muscle mass. So once again, I appreciate it. You can check more videos like this out from me, Andy Galpin, my website, andygalpin.com. And if you felt like you've learned and earned some value here, I would certainly appreciate a contribution of $1 or $2 to my Patreon account. That's Patreon, patreon.com/Andy Galpin. You can also check this out on all of my various social media, my Instagram account at Dr. Andy Galpin and such. But for now, thank you for your time, and let's make the world a better place. Cheers.